2D matrix, and here inside the matrix you have these shipping costs per unit. Here 1 unit is 1 truckload. So the objective is to find out the minimum cost. You wanna solve for the lowest cost that will allow you to satisfy all the constraints and supplies. So these are the outputs, so the supply capacities. These are the demand, so the number of units required. Demand required. So this will be part of your demand constraints, and you have your supply capacities, which will be part of your supply constraints. So same setup here. No, so the whole chapter is basically saying you can solve it with the simplex method we saw before. That's the more standard way or traditional way. But for transportation, we can use that as a basis, and there's going to be somewhat more streamlined, so more efficient algorithms based on the simplex to help you solve transportation. So we'll go over some of those algorithms and to solve transportation problems. So basically a different kind of another set of algorithms which are similar to the simplex but not exactly the same. So that's the whole content in this chapter. But the setup is the same. You have seen this in the first week. So we can describe this network in a diagram like this. So we have the 3 sources, the canaries, the 4 warehouses, which will receive the units, and then you have all these combinations of the shipping costs. That'll be the shipping cost per truckload. Again, so you can represent a distribution network like this with the network diagram, and then in the next chapter, chapter 10, we're going to look at some network problems. Okay? So you'll see this kind of diagram with these notations more often for the next chapter we look at. But here, transportation network can also be represented this way. Okay. So these are the objective functions and the constraints. Right? So again, we saw this before. Right? This is the total cost. You have the coefficient in the objective function. That would be unit cost for 1 pair of source and destination. Right? Right? So the x's are the number of units. So these are the decision variables that we have to decide how many units to ship for every pair of source and destination. Right? And the not every pair will receive units. Some pairs of source and destination will have no units, so 0 being allocated. Right? So, units to ship between each source and destination pair. Those the decision variables, and we have to satisfy the supplies and the demands. Right, so we have the n canaries. So the decision variables xij will represent the number of units to be shipped from the source I to destination j. Okay? And then all the sources with all the m canaries. Right? If you add all of them together, that's going to give you the supply for that particular canary. What's the maximum that can be produced out of the canary I. Right? The total shipped out of that source or canary must be equal to the capacity of that source. Right? Then with a demand constraint for every destination, the total demand or total units received must be equal to the demand needed for that destination. So this should be same as what we saw in first week. And then we have the non-negativity constraints. We have the 12 decision variables. All of them must be non-negative because we can't ship negative units. Right now in the network chapter, you see, it can be sometimes can be negative, but here for the transportation problem, the standard form is that they must be all non-negative. Okay. So we have the 12 decision variables because we have 3 sources, 4 destinations, so 12 pairs of the cities, and then there's 12 decision variables, so 12 numbers to solve for. And the objective is to minimize the total cost. The standard form of the transportation problem. Feasible solution. So there's some properties. So we'll just go over these, but then it's actually just nothing new here. The total supplied out of the all the sources together must equal to the total received by all the destinations. This is the feasible solutions property. So this is saying that we're not going to produce any extra. So that's one of the feasible solutions property. When you have a transportation problem, you should make sure you set up a problem like this, such that the total supply created or shipped from all the sources equal to total demand received. Right. So that's one of the feasible solutions property for the transportation problem. There's the requirements assumption. So every source has a fixed supply, so you're not going to change that. When if your business, you run this over time, we assume the supply capacity of each source is not going to change. Okay?